We have the honor and privilege with the Tech Bros, whose mission is to increase the number of all-female, all-technical startups coming into existence. Today, we'll experience an interactive, hands-on workshop that utilizes math, logic, and computer science. We'll also learn more about what happens when code meets the concept of infinity. To lead the charge, we have two guest speakers from the Tech Bros. First, we have Millet Gallo out of Oxford, England of the UK, United Kingdom, who is not only one of the co-founders of the Tech Bros, but also has a PhD in mathematics and an opera singer. Side note, Google Spider Pig opera, you'll hear her voice. She's like the third result. Okay. Also based out of Oxford, England, and fellow co-founder of the Tech Bros, we have Sydenham Simpson. She worked as a former data scientist and one of a handful of former students selected as a Google DeepMind Scholar, which is super cool. Needless to say, we have two incredibly talented and brilliant co-founders who will guide us today. And if you have any questions, feel free to ask throughout. It's super chill. It's more like a discussion, hangout. But we'll probably also have time to answer any questions you may have. So enough of me talking. The Lion King intro is down. Please, Millet and Sidanam, please take it away.
Cool. Let's just, I guess we'll share our screen. And can people see this?
Yes.
Cool. So, hi, we are from the Tech Bros, as Jonathan very kindly has mentioned to everyone. We've been going for about a year, and yeah, our mission is to back female-founded tech startups, so startups with entirely female and entirely technical founding teams.
So essentially why we exist. So the VC landscape is incredibly skewed. So majority of the funding goes to all male teams, with only 2% of VC funding going to all female teams. So we really exist to sort of shift this balance and sort of shake up the industry. So yeah.
And basically, we've done a bunch of events across the UK. We've done our first event outside the UK a couple of weeks ago at New York Tech Week, which was a lot of fun. And we are launching our first Accelerator program this summer. So a little bit about us. I think actually Jonathan gave a pretty good intro. So I have a background in opera maths and BC.
And I have a background in machine learning and also economics and statistics.
Cool. So welcome to Coding at the Edge of Infinity. Without further ado. So first of all, the sort of first section of this is basically about understanding infinity and what infinity is. So if you have any questions, do put them in the chat. I'm worried I won't be able to see them, but
no, yeah, it will pop up.
Hopefully it'll pop up. Okay, cool. So if you have any questions as we go, do just hop in. First of all, infinity. It's not a number, but we often treat it as a number in maths. But it is more of a concept, if you will. So the reason that it's interesting is just that it behaves very, very counterintuitively and very unusually. So you can kind of add to it and you can double it. You can do all kinds of fun things with infinity, and it doesn't change, or it might change in a way that you're not expecting. Cool. Okay,
we just double checking the chat.
Yeah.
Seeing things on pop up. Okay.
Cool. Let me. Okay. So we're going to start with something called Hilbert's Hotel. So this is a concept by one of the best mathematicians, or one of my favorite mathematicians, Hilbert. So basically, imagine that you have a hotel with infinitely many rooms. And this is just, again, to get an understanding of how infinity works. So you have infinitely many rooms. And tonight, this hotel is full. So there is someone staying in every single room. So what happens when a new guest arrives and is like, hey, I want to stay here too. Where can we put this guest? Is there room for this guest? It would be good to actually put in the chat, do you think there's room for this guest? And can you think of a way to make room for the new guest? How do we see that? Here it is. Don't all answer at once.
Yes, room,
yes.
Pondering, yes.
Okay, so there's a very, very easy way to make room for our new guest here. And what it is we ask we ask everyone to pack up all their things. It's not easy for each individual other guest, but whatever. We ask each guest to pack up their room and move to the room that's one number higher than the number that they were staying in. So for simplicity, let's say we number these guests 1, 2, 3, 4, 5, all the way up. And you can see there's a ... here. In maths, that just means continues until infinity. So whenever you see ... you're like, well, that's an infinite set suddenly. So basically every person moves one room higher. And here we go. Room number 1 is suddenly free. And our new guest can slot right in. So you can see that you can have infinity and you can add another person, another number, and we still have infinity. Okay, what if we have 3 people? Now a bunch more people have come in and they also want a room. Hang on, we've got a chat. Is this effectively, I don't know what LIFO is.
Last in, first out. I don't think this
No.
relates to the concept of last in, first out. No.
I don't think so. No. What is last in, first out?
So if
Isn't that when people get fired? I feel like we may go off track here.
this is going to be a rabbit hole. Yes.
Yeah, exactly. Yes, Aspen, you are correct. So basically, we can move them all up further along. So yeah, we move them all 3 numbers higher than the room that they came in. So anyone who's just joined us, we have a hotel with infinitely many rooms and infinitely many guests, but some new guests have shown up. How can we make room for them? If everyone gets out of their room, clears out all their belongings and moves up a couple of rooms, then suddenly room number 1 is free, room number 2, 3, and 4 are free, and these new people can have a nice room to stay in. And you can see how once you start dealing with infinity in maths, suddenly anything finite, it's like, oh, that's just the same thing, right? Like we can fit in 1 person, so we can fit in any number of finite people. 10 billion people show up, cool, we just move everyone 10 billion rooms up and we're good. So yeah, so here we can see how you could write this, 4 plus infinity equals infinity. Just a little note, this symbol here is never used in maths, but it's actually, that's not true. It's never used in logic, where you would typically be dealing with this kind of thing, but we'll use it for now because it's the one most people are familiar with. So yeah, you can see that you can add 4 people. You still have infinity, all good. What about, and as someone said in the comments, you can add n where n is any finite number. Okay, what about if we had an infinite number of people who suddenly want a room? What do we do? So you have, for each room, someone shows up, again, an infinite number. So you have 1, 2, 3, 4, 5, like the same sort of arrangement that you have of people in the rooms. You have a new set of people show up, so effectively double. How are these new people going to fit? Does anyone want to kind of venture a guess in our comments channel? We can move n plus infinity. So we actually can't, in the same way, fit everyone in at the start because there just won't. It'll keep going. Yeah, we can't just fit them in at the start in the same way. We sort of have to clear a specific room for them. Infinite. Yes. So basically, there's a simple way to do this. So it's not like a trick question. Like there is a way to do it where you can kind of see exactly where everyone will go. And that's the thing. Often when dealing with infinity, it's very much a case of turning it into something that we understand. And so what we can do, I think I'll move on because I'm assuming people want to know. What we can do is we can tell every person. So let's say you are person number 1 in room number 1. Now you're going to move to the room that is double the number of your room. Yeah. They're all coming in at once. Yeah. So we've got infinitely many people. We've got this set of pink people who are already there, and then we've got this set of purple people. They're new. How are we going to fit those people in? Whilst we can move people around different rooms, but we got to keep them all there at the same time. Can it be done? And the answer is yes. So we take all of these pink people who are already in the rooms, and we say, okay, get out of your room and go to the room number that was double what your previous room number was, right? So person number 1 goes to room number 2, 2 goes to room number 4, and so on. And look, infinitely many rooms have just become free. How fun. So these people can now come in and fit, and suddenly we have room for twice as many, infinitely many people. So that effectively shows we can have 2 copies of infinity. And you can do this with any finite number of copies of infinity, and then there are ways to do it with an infinite number of copies. So basically infinity just does not behave in any way like we would expect, which is what makes it fun. So now we have another question. Oh, sorry. Yes, any questions in the
mind blown.
Exactly,
Yeah.
it's really fun. So now the next question is, okay, so we can take infinitely many guests and we can take multiple sets of infinitely many guests and add them in, can we have more guests than rooms? So is it possible in this situation, we have this hotel and we have these rooms and they're numbered 1, 2, 3, 4, 5, and you go all the way up. Is it possible to have a number of like an infinite set of guests that don't fit in this hotel? So you can probably tell by my tone what the answer is going to be, but I would love if people could still guess what they think in the comments, because we want to keep it interactive. How do I get to the comments? Here we go. Oh, okay. Well, I've just revealed the answer by accident. So yeah, the answer is it is possible to have more guests than you have number of rooms. Does this make sense as a question?
Anyone else?
The
Yes.
maths is nothing. Okay, cool.
Don't be shy, y'all. Don't be shy.
Cool. So yes, it is possible to have more guests than rooms, even though we already have infinitely many rooms. And how do we do this? So imagine we have a bunch of guests. Since I'm the one showing that you can have more guests than rooms, I'm allowed to kind of define these guests how I want to, right? So I'm going to give each guest a number. So before, you'll notice each guest had a number. It was 1, 2, 3, 4, 5, and you had this set. And then when we took a second set of guests, they were also numbered 1, 2, 3, 4, 5, and so on. But these guests are going to have way more fun numbers. So each one is going to have a recurring infinite decimal expansion. So you may be familiar with these from kind of the number line, the real numbers, like 3.33333 is like 3 1/3, that kind of thing. But you can have any sort of infinite decimal expansion will sit somewhere on the real number line. And it can end up repeating, it can end up not repeating. The point is it's just an infinite expansion. So for each person, they're going to have their own infinite decimal expansion, and that's kind of their label, as it were. That's their number. Now, these can all fit if we can assign each of these people to a room. So we could give, for example, this person 1.365428 whatever. This person gets room number 1. And then these other people get room 2, room 3, room 4, and so on. So the point is, if we can kind of assign a room to each of these people, then they will all fit. But I can prove that they're not going to all fit. And here's how. So first of all, we're going to write them out like this on the side, just for you'll see why in a second, but it's gonna get much simpler in a minute why we've done it like this. So imagine that the rooms are kind of labeled 1, 2, 3 all the way down, and next to the room we have the person who was assigned to that room. So as we can see, 1.365 is assigned to room 1, and 5.76766 is assigned to room 2, and so on. So we've assigned them all, and we've got all of these different infinite decimal expansions for each person, and there's infinitely many of those, and there's infinitely many rooms. So the question is, can I find someone with an infinite decimal expansion who hasn't been represented, who isn't number 100 or number 1 million, just doesn't show up on the list at all? And if we can find that person, then that person doesn't have a room and therefore doesn't fit. And here's how we find that person. So here's a person that I'm going to describe for you, and I'm going to prove to you that they don't have a room. So they have their own infinite decimal expansion, just like everyone else. I'm going to call it A, point B, C, D, E, F, G. And before we decide what A, B, C, all of these letters, all these numbers are going to be, pay attention. I want you to pay attention to, for room 1, the very first number here. For room 2, the second number. For room 3, the third number in the decimal expansion. For room 4, the fourth number, and so on. So you get this kind of diagonal. And what we're going to do is we're going to choose a number here so that A is not equal to 1, which is this first number here. B is not equal to 7, which is the second number here. C is not equal to the third number here, 8. D is not equal to the fourth number here, also 8, right? So we're going to pick something that is not equal to the first number of... So the first number of this decimal expansion isn't equal to the first one of this one. The second one here isn't equal to the second one of the second person. The third one is not equal to the third number in the third person's kind of decimal expansion, and so on. So this person's number is going to be, let's choose something, right? So 7, that's not equal to 1. Something that's not 7, 3. Something that's not 8 could be 2. Something that's not 8, again, could be 1. So we've just chosen this number. With infinite, isn't that always inevitable? Isn't what always inevitable? No, you may not be missing the point.
Oh yeah, I'll just unmute, I guess.
Yeah.
I'm mainly trying to keep up. I'm real bad at this kind of stuff, and I'm trying to get better. I work with like Linux and system administration and server stuff, so I'm like in the command line, and so I'm thinking of this from like development and programming logic kind of perspective, and I'm thinking, okay, well, if you're looking at each individual digit and its placement and the number, and it's infinite, and you're doing a logic match of does not equal for each character place, wouldn't you persistently always be able to find instances of this, or I'll leave it at that. I guess I may not even be wording my thoughts correctly
No,
on
no, I
this.
think you might. I think you might have just discovered the proof of this, right? So the whole point is, yes, there will always be a number here that isn't on this list, right?
Oh, okay, okay.
Is that what you meant?
I think so. Yeah,
Yeah, yeah, yeah. So that's that. Okay, so that's you understanding it. So we're all good.
excellent. Great.
Um, so yeah, so basically we're choosing a number that's not going to be on this list, and we choose it to not equal. We know it's not equal to this first one because the first digit isn't equal to the first digit. We know it's not equal to the second one because the second digit isn't equal to the second digit. We know it's not equal to the third one because the third digit isn't equal to the third digit, and so on all the way down this infinite series of digits. And so we know that this person here, who's really excited to stay in the hotel, actually doesn't have is not on the list for the hotel, which is really sad for our sad little friend here. So the point is, when you have, and this is just kind of a very classic proof within maths, and actually something that you would learn probably in your first year of undergrad, to show that some infinities are bigger than other infinities. So what this here is called on the left, these numbers 1, 2, 3, all the way up, this is what's called countable infinity. So basically you can count it like 1, 2, 3, all the way along, and you can have two copies of that infinity, and that's still countable. So that's why we could kind of fit all those people in, and you can have infinitely many. You can have countable infinity times countable infinity, and you still end up with countable infinities. You could fit all those people in. But as soon as you get uncountable, as soon as you get to the real number line, suddenly they're not going to fit. And this is how. So if you're interested in what this proof is, it's called Cantor's diagonal proof. I'll write it in the chat. And if anyone wants to look that up, that is what you look up for this. But this is our little hotel example of Cantor's diagonal proof. So basically that this uncountable infinity, that there are infinitely many more numbers in an uncountably infinite sized set or collection of objects than there are in a countable. Yes, we have to do another question. What is a real number line in this context? So the real number line is the set of all infinite decimal expansions. So exactly how we defined these people's ID numbers, essentially. So imagine each one has this infinite ID number. If you have every single possible number of those, that is the real number line. So you'll probably seen the real number line. It's kind of this continuous, and you have every rational and every fraction, and you have pi, and you have all of that. So not every infinite decimal expansion has a cool name like pi. Like you can just have pi and then you just change the one digit, and then that's another infinite decimal expansion. You can do that for every single number. So anyway, so this is our uncountably infinite set, and what's really fun is that there aren't just two sizes of infinity. So you have countable infinity is known as Aleph 0, and that's the size of that infinity. That's where I say, like in maths, we don't use this symbol so much. I think they use it maybe in certain areas, but not in logic, not in set theory. So for our little baby infinity here, we have Aleph 0, and that is the countable infinity, and that's like the sort of the nice easy example often. And then Aleph 1 is your sort of first uncountable infinity, and then you have infinitely many above that, and then you have something called large cardinals, which are even like huge. They are way bigger than these infinities. So it's kind of like a whole universe within our sort of mathematical sort of systems. And it's kind of as mind-blowing as when you look at images of the real universe and you just realize how small you are. So I think I'll leave it there on understanding infinity. And I would definitely encourage people to kind of look into this, even if you're someone who doesn't love maths or who has never really got along with it. It's very different to kind of, calculating the gradient of a curve or something like that.
Cool. So essentially now we've spoken about, I guess, the theoretical aspects of infinity, and to formalize it, we actually, need formal systems. So this is where now we relate the concept of infinity to coding, computer science, machine learning, that sort of thing. So essentially, we can have programs, like computer science programs or computing programs, and even really, really small ones, and they can take longer to execute than the lifetime of the universe. And some programs might not even finish executing at all. So an example of this would be a while loop. So if you're familiar with Python coding or just coding in general, you'll know that if you have this sort of while loop and you say like while true, just continue executing. And this is what we call an infinite loop. You haven't given it a stopping condition, so it'll just keep executing until, I mean, eventually your computer crashes. And we also have sort of real life examples of when this would occur. So we can't necessarily figure out every possible like chess simulation before like, the universe ends. With a lot of encryption codes, so basically how like information is stored securely online, like there's a lot of combinations that you would have to go through to crack all these codes. Of course, with like the invention of like quantum computing, that's something that poses a risk to encryption, but as it currently stands, it's something that will take like forever to crack. And then also when you're calculating super large prime numbers, I'm aware that on the screen right now, the number 1 is not a prime number. And it's also not a large number, but it's just a joke.
The little maths joke.
So then basically this takes us to something called the halting problem.
Yeah.
So do you want to
Yeah, so the halting problem kind of links these two concepts. So basically, can we write a program that can check whether every single other program will eventually stop or whether it won't stop? This was originally posed by Alan Turing in the 30s, I think. And the answer, wait, do people want to guess the answer or do you know the answer?
I'll wait for you to guess.
We're going to give you 30 seconds. Don't all guess at once.
We'll sit in awkward silence. My reflex is yes.
But I'm guessing no.
I'm guessing no. Aspen says no.
Well, let's continue because I feel like sometimes the way I present this, it's kind of obvious what the answer is going to be, but not necessarily why. So the answer is indeed no. You cannot write a program that can check whether any other program will stop. It would be very, very convenient, wouldn't it? Because then you would know whether you are going to end up in one of these horrible scenarios where the program just runs forever. Oh, hang on.
Quickly check the chat.
Yes. Check process. Wait, I don't understand.
I don't understand that. Check process ID exists? What do you mean?
It's just I was being silly because in Linux you could do that by checking to see if the process ID of the program that you ran was still operating, and it's not. But I know that's not what you're talking about here.
Yeah, okay, fine.
I thought it was some sort of joke that was going over my head, but cool. So the answer is no. So basically, let's imagine we have a program like this, and we're going to call it halts. And this program is going to return true if basically your program. Oh, hang on. Let's ignore the fact that ignore this input. That should have not been there. I was making a simplified version. So if this program halts, then it returns true. If program runs forever, then it returns false. Okay, so let's assume that this exists, and this program is called halts. Brilliantly named. So now we're going to define another program. This program is going to be called paradox. So paradox, if paradox itself halts, so if paradox halts, then it's going to loop forever. It's going to do the little pass thing that Sedinam showed us in the previous a couple slides ago. So basically, if this program does halt, then it's gonna not halt. And if it doesn't halt, then it's going to return that it halted. So this paradox program is gonna, because we're using halted on the program itself, whatever it does, it doesn't do. And whatever it doesn't do, it does. And so the fact that this program could exist, therefore means that this can't exist. So it's basically asking, am I going to halt? And then if the answer is yes, then it goes, well, I'm not going to halt. And if the answer is no, then it goes, I will halt. So that's basically how we can define this. And that's a nice, neat little way to show that the halting problem is not really a problem, because we know that it's not possible to create this program. So yeah, either way, the program here is wrong, basically. And there's just no way for this program here to be correct. So it's very similar to, you might have come across similar paradoxes like, I am lying right now, or this sentence is false. It's like, if it's false, then it's true. If it's true, then it's false. But this is just a nice little way to show that this is not possible.
Cool. So then sort of like relating this concept to machine learning. So a lot of the time, machine learning models or systems have to operate in a world where we don't have finite data, or like the data never ends. So we keep having to learn from new data, if that makes sense. So some examples of this would be if you're looking at real-time streaming, as more information comes in through streams, you're going to have to adapt that into your model system. The same with the internet, it's ever expanding. There's more information getting added. So if you're training anything that relates to web content, again, it's similar to streaming. You'd need to sort of integrate that information regularly. And then things like human behavior. I think that, if you're modeling anything based on how someone interacts with a piece of code or a piece of content online or whatever it may be, that's a consistent stream of new information that you need to be able to integrate. And it is essentially like an infinite amount of information you'll keep getting. And essentially, what we then see is that these models need to make decisions before seeing everything that it has to like process, if that makes sense. And essentially, we can sort of coin this as, I mean, it's not an official term, but essentially what we've coined it as is that we're learning under infinity, essentially. So some like more tangible examples. So a self-driving car, for example, it needs to constantly react to the environment around it, and that's forever changing. And there's no finite set of things that could happen at a specific point in time. So yeah, basically, it's kind of unknown. Again, it's similar with like stock trading agents in markets that are never ending. And then open world games or simulations, similar to like the chess example, the like chess simulations example. And then chatbots learning continuously from conversations. So in the chat, so long as new news data and research comes on models. Yes, yeah, that is correct. And then chatbots constantly learning from conversations, continuous conversations. Cool. So then this presents some challenges. So the first one being that it's impossible for the models to memorize everything that exists. I'm just checking the chat again. Do you think that this contributes to the cognitive decline or dementia? It could be. I'm actually not entirely sure, but I mean, I think it is a possibility for sure. Yeah. So the challenges. So it's impossible for models to memorize everything. It's also then, sorry, this is
I know,
not,
it's
yeah. Then learning it never reaches a point where it's like, I've finished learning everything that exists, because there's constantly more being added. And then again, in concepts like reinforcement learning, you'll hear this idea of exploration. So the exploration never ends, and there's no ground truth. So there's nothing. If we had a finite set of numbers that it was learning, for example, that we could root that in sort of, this is the truth and you need to learn the truth. But because there's constantly new things being added, there's no sense of what is the actual truth, if that makes sense. And then basically we have machine learning techniques that we then can use to deal with the fact that things need to be constantly updated and that it needs to learn from an environment that's forever changing. So we have, this is just a list, and I mean, I don't necessarily have to go through it piece by piece, but there's reinforcement learning that basically learns from each interaction over time. There's something called online learning. So you consistently updating your model with new information and you're doing it sort of one point at a time. There's things like Bayesian learning. So you have prior knowledge and then you adapt the algorithm or the model based off of new information that you're learning. And then there's things like meta learning. So you could have essentially a model that then learns how to learn new information. And there's a whole host of other techniques out there. Okay, cool. So I feel like we basically we have an example for you to try out, a notebook. Do you want to stop
I was just
sharing
gonna
here?
say, yeah, or do you want to,
I just need to drop the link in here of the notebook.
hang on. I think you could, because it's sharing just this screen, right?
Yeah.
Yeah, so why don't we drop it in the chat?
Okay, but I need
You airdrop me the,
yeah.
sorry guys, bear with us, technical difficulties.
1 second.
All good, no worries.
Airdropping a link in this moment. Okay,
Cool.
just open that. Let's see.
And if we shove that in the chat.
That should work. Yeah.
Cool. Let us know if this link works.
But essentially, so what this notebook is, it's talking through something called the collats. Is it collats?
Collats? Yeah, I don't know.
Don't know the pronunciation.
It
Conjecture, which means
works.
okay, awesome. Yeah, it's just a brief function, the collats function. And what this states, the conjecture, is that no matter what positive integer you start with, you'll eventually reach 1. So this is sort of like the pseudocode for it. So you can take any number in. If it's an even number, then you divide it by 2. If it's an odd number, you times it by 3 and then add 1, and then you repeat this process. So we encourage you to just try it out with a couple numbers. You can uncomment the comments in the notebook and print a couple numbers. And basically, our question to you is that will you always reach 1 when you try out a different sequence or a different number each time? So we'll give you a couple of seconds.
Why don't we give you 2 minutes and then
Seconds, you
a
minutes.
couple seconds. And then what would be great is if you could drop in the chat
What you think?
what you get, yeah,
Mhm.
what you think, and also what number you entered and how many steps it took to reach 1 if you reached 1. Or if your computer crashed, also let us know. How many steps did you get?
Yeah.
345
That's a
steps.
lot,
What
yeah.
number did you start with? What was the sort of first input in order to get to? Oh, that's quite a large number. That's probably why it took
Okay,
345
yeah,
steps.
that makes sense.
But it still got to 1. She took her time. You guys are starting with such high numbers. I'm like,
Yeah.
I'm literally
I
like, what
started
if
with
we
like
start with 2?
2.
2 gets you to 1.
Yeah. Yeah. Okay, that's super interesting.
What was what's sort of the highest number of steps that we think someone's gonna can anyone get higher than 345?
What do you mean
What
by
is a vanishing
algorithm? Vanishing.
Something like if I keep going in increments of 10, 5, 12, 10, 24, et cetera, it gets right to 1, but I feel like that's missing the point, possibly. I don't know.
As in,
So essentially what would be
is the question that you're asking, is it like a decreasing function that always gets closer and closer to 1? Because we know it's not the case, right? Because it'll go up and down, because if you hit an odd number, then you'll go up again.
so yeah, so essentially what would be interesting is if you like have a plot of
Yeah.
your values that you get, essentially.
So like, let's say that this was the example that I initially thought of, right? Is if we start with the number 20 and then that gets halved to 10, that gets halved to 5, and then but that's now odd. So then we multiply that by 3, we get 15 plus 1, 16. So now we're on 16. So then we halve that to 8, to 4, to 2, to 1. Okay, that gives us 1. That's a nice, neat example. But if you start with, the point is you can hit an odd number and then you can suddenly end up going quite a lot higher. And then you go down to another odd number and you go up higher again. So the idea is we think it's going to eventually get to 1, but we don't know.
And essentially, like, the thing here is that, like, a lot of the time, I'm sure with a lot of the numbers you're trying out, it does actually get to 1. But the thing is that we don't know if every single number, no one's ever figured out if every single number would it get to 1.
412 with decimal.
Oh,
What does that mean?
what do you mean with decimal?
Oh.
That with certain numbers, if we omit a 0, sometimes it takes more steps. Oh,
That is
interesting.
interesting.
Yeah.
Oh, is it the number
oh,
of steps it's saying it took? Maybe that's times 10 to the sun. Maybe that's like a huge, huge number of steps.
Or is that the input that you gave it? No, I think this was the input with
Oh.
decimal, and then it took 400.
Okay, yeah. It
Yeah.
has to be a whole number.
Yeah. Ah, interesting.
That is interesting.
Yeah. Yeah. I mean, it's just a little activity, but basically we don't know if every number will always reach 1. Yeah.
Cool. So just to sum up what we've learned today, like the zero division problem leads to infinity, but what infinity really means. The zero division problem is a whole kind of separate thing. It's sort of that tends towards infinity, but it doesn't actually equal infinity. But that's a little rabbit hole we can go down if we have time, but we don't really, because we've got 5 minutes. Actually, this timing has been perfect, so
Yeah.
I'm very happy with we're right on our last slide here. So just kind of to sum up what it is that we've learned today. So infinity breaks intuition, as we have seen at the beginning. So maths can show us kind of what's possible, and computer science can show us what's not possible. And we really feel like code can be where you can take abstraction and reality and kind of put them together. And that's why things like complexity theory are so interesting. So basically, kind of to summarize, you don't need infinite memory to think infinitely. But if you understand the limits of logic and of machines and of maths and of code, then it can help you ask better questions and understand the world and everything in it better. And we're going to leave you with a little quote here at the end. For every problem that can be solved, there's one that can't, and that's the beauty of it. And we've got another quote for you, just a bonus quote. You can't count to infinity, but you can count on it showing up.
Thank you so much.
We hope you enjoyed.
One more time, could everyone in the chat please say thank you for the Tech Bros giving us their time to put together this fantastic presentation. My brain hurts. I was paying attention. I feel like I need a beer to kind of like take off the edge. There's a lot in here, but I did learn a lot. Did not know that there could be so many different kinds of infinity. Remarkable. Do we have, I know we only have a few minutes left, but are there any other like last minute questions before we disband here?
Enjoying the comments.
Yes.
This is a funny crowd we have. I like it.
Yeah.
Yes. Okay. If they would like to reach out to you just to have any follow-up questions, what's the best way for them to contact you?
We have our email address here.
We'll tap it in the chat now.
Yeah.
Okay, great. Let's shoot them an email. I'm sure there'll be so many other questions. But yeah, thank you so much. Also, again, a reminder for those who did come late, we will be uploading this video to YouTube, so you can rewatch it. I may need to rewatch it in slow motion or slow it down maybe like 2 or 3 times. There's a lot of information here. So, but anyways, hope everyone has a good rest of the week. And again, thank you so much. We'll do this again
Thanks so
soon.
much.
Thanks for that.
Bye.